Okay, we're going to start Chapter 5, Trigonometric Identities. So in 5.1, we're going to learn all of the basic identities, and then we're going to put them into practice. So let's first get through what they are. So an equation is an identity. So what makes an identity? It's when the left side is equal to the right side for all values of the variable for which both sides are defined. So an identity is something that you know to be true based on the left side always being equal to the right side. One of the identities that you already know is the Pythagorean theorem. We know that in any given right triangle, a squared plus b squared equals c squared. You know that to be an identity for all values on that triangle. Okay, so basic trig identities. You already know half of these. First, we're going to talk about the ones that you already know. But it says when simplifying, solving, and verifying trig identities and equations, there are several basic identities you're going to need to know and be able to use. So first of all, the reciprocal identities. The sine function, the sine of theta is equal to 1 over the cosecant of theta. We know this. But then vice versa, we know the cosecant of theta is 1 over the sine of theta. We know that the cosine of theta is 1 over the secant of theta. And the secant of theta is 1 over the cosine of theta. And we know that the tangent of theta is 1 over the cotangent of theta. And the cotangent of theta is then 1 over the tangent of theta. And those are ones that we've already used in various examples in Chapter 4. The quotient identities, these are ones that you should know as well. We've already dealt with this a little bit. The tangent of theta, we know that the tangent is y over x, and we know that y is the same as the sine of theta, and x relates to and is the same as the cosine of theta. So we know the tangent of theta is equal to the sine of theta over cosine of theta. Then if we take the reciprocal, we can say that the cotangent of theta is equal to the cosine of theta, which is your x, over the sine of theta, which is your y. And all of these we should know from Chapter 4. They should not be new. Okay, now the rest of these, this second half, these are going to be brand new, but hopefully we can make these make sense to you by kind of diagramming them out and talking about some of the things that we already know to be true about right triangles and theta all around the circle. So we're going to start with Pythagorean identities. And the thing that you think about when you think about Pythagorean theorem or Pythagorean identities is, of course, that Pythagorean theorem that we talked about, that you have known about since Algebra 1 or even middle school. So let's take a triangle. Actually, I'm going to erase here. In the first quadrant. So if we have this triangle in the first quadrant, we're going to call that theta. Opposite of theta, we're going to have the y value, because remember, to get to that ordered pair, that point up there, that would be our y value. Along the base is our x value, and then we have the r value, which is our hypotenuse. And we know the Pythagorean theorem holds true, so we know that r squared is equal to x squared plus y squared from Pythagorean theorem. So our first Pythagorean identity that we're going to show you comes right from this. Actually, there are really only 3 Pythagorean identities. 1, 2, 3. And then it looks like there's 9. There are not 9. There are 3. And then the 2 underneath are simply manipulations of the first one. So there are only 3 Pythagorean identities, but the 2 underneath, again, are just manipulations of the one on top. So let's say we go back to this equation, r squared equals x squared plus y squared. Hopefully we are okay with the fact that I could divide everything, every piece of this function by the same thing, and it would not really affect my graph, or not my graph, it would not really affect my equation. So for example, if I do something to one part of the equation and then I do it to the whole equation, to every part, I'm really okay. I haven't broken any math rules. So what we're going to do is we are going to first divide every term by r squared. Doing the same thing to every part of the equation is okay. So if I do that, I have created r squared over r squared, which is 1, x squared over r squared. Well, I'm hoping you recognize x squared over r squared because we learned that, if you remember, cosine of theta when the radius was not 1 was x over r. So if I have x squared over r squared, I really can replace that with cosine squared of theta. Then you learned that the sine of theta was really y over r when you're outside of the unit circle, the opposite over the hypotenuse. So I could replace y squared over r squared with sine squared theta. So taking the Pythagorean theorem, r squared equaling x squared plus y squared, I can divide each part by r squared, and I would get 1 equal to the cosine squared plus the sine squared, or sine squared cos squared, either way. And this is going to be our first Pythagorean identity. Now, it's typically written like this: sine squared theta plus cos squared theta is equal to 1. That's our first Pythagorean identity. So the two beneath it are simply solving for sine squared and cos squared. So I can then say that sine squared theta would equal 1 minus cos squared. And remember, subtraction is not commutative. Order absolutely matters. So 1 minus cos squared is equal to sine squared. And if I solve for cosine squared, I could say that cosine squared theta is equal to 1 minus sine squared theta. So there's one Pythagorean identity written 3 ways. Okay, I'm going to go back and erase. Now you don't need to know where these come from, so I'm going to erase this. You're going to have to know them, but you don't have to prove them every time. So we're going to go back to my equation. R squared equals x squared plus y squared. And this time, we're going to divide everything by x squared. So let's do r squared over x squared over x squared, and y squared over x squared. So r squared over x squared. Remember that if cosine of theta was x over r, then r over x was the secant of theta. So I really have, let me change colors here so this stands out, I really have the secant squared of theta right there equal to x squared over x squared is 1 plus y squared over x squared. Well, remember that tangent of theta is y over x, so y squared over x squared is tangent squared theta. And this is our second Pythagorean identity. And I'm gonna write it this way, just how it's standardly written or said. Tan squared theta plus 1 is equal to secant squared theta. And that's where it comes from, the right triangle dividing everything by x squared. And then looking at those ratios and what they represent with the trig functions. So the two beneath this are manipulations of this equation. So if we were to solve this for tangent squared, I would say that tangent squared theta is equal to secant squared theta minus 1. And I could then say, if I solve for 1, I could say 1 is equal to secant squared theta minus tangent squared theta. And that's the second identity with a couple of manipulations. Okay, and then you probably already guessed what we're going to do for the last one. We are going to divide everything by y squared. So as we do this, we're going to divide by y squared. And so r squared over y squared, well, we know that sine of theta is y over r, so cosecant is r over y. So what I have is cosecant squared theta equals x squared over y squared. Well, that would be, if I have x over y, that's cotangent of theta. So that would be cotangent squared of theta. And then plus y squared over y squared is 1. So my third Pythagorean identity is that cotangent squared theta plus 1 is equal to cosecant squared theta. And the two beneath that are manipulations of this first equation, so I could say that cotangent squared theta is equal to cosecant squared theta minus 1. And I could also say that 1 is equal to cosecant squared theta minus cotangent squared theta. Okay, so although it looks like 9 Pythagorean identities, there are only 3 main Pythagorean identities. These are the ones you want to memorize, and then be able to manipulate them, think about them and manipulate them to recognize the other 6. Okay? All right, the second type of identity we're going to talk about are co-function identities. So co-function identities are kind of easy to remember because they go with their function and their co-function. The first one we're going to talk about is the sine of theta, and the co-function to sine is cosine. Now, before I write that in there, I want you to think about something. Think about the sine of 30 degrees, which is something we should know. Remember, that's my favorite. The sine of 30 degrees is equal to the co of sine, or the cosine of what? Well, I know the sine of 30 is 1/2. So hopefully you remember that the cosine of 60, the other one, is 1/2. Well, 60 we can think of as coming from 90 minus 30. So our first co-function identity is going to be the sine of theta is equal to the cosine of 90 degrees is the same as pi over 2 minus theta. So I could say that the sine of 30 degrees is the same as the cosine of 90 minus 30. If you look to your graphs of sine and cosine, tangent, cotangent, secant, cosecant, they are 90 degree shifts of each other. So the sine of theta is the same as moving theta to the left, to the right, pi over 2. So if I take then and reverse this, I could say the cosine of theta is equal to the sine of pi over 2 minus theta. Because again, if I use a number to kind of wrap my head around this, I know that the cosine of 60 degrees, actually let's use 30 again. The cosine of 30 degrees is the same as the sine of 90 minus 30 degrees, or 60 degrees. They are both the square root of 3 over 2. So they are 90 degree shifts. If you shift one of them 90 degrees, it will be right on top of the other, and they will share the same values. So that being said, it works the same for the other functions as well, being co-functions. We can say that the tangent of theta is equal to the cotangent of pi over 2 minus theta, and you can check that out with 30 degrees. If I know that the tangent of 30 degrees is equal to the cotangent of 90 minus 30, let's check that out. The tangent of 30 is root 3 over 3, and if you go to your unit circle and you put the x over the y, you're going to see that the cotangent of 60 is also root 3 over 3. So you can verify all of these identities by using your unit circle, plugging in some values, and checking those out. Okay, so let's fill in the rest of this. The cotangent of theta then is equal to the tangent of pi over 2 minus theta. And then our last two cofunctions are secant and cosecant. So we can say that the secant of theta is equal to the cosecant of pi over 2 minus theta. And the cosecant of theta is equal to the secant of pi over 2 minus theta. Now, one important thing that you might be prone to getting confused is the order. What's really important, you know that subtraction is not commutative. You cannot reverse it without making some other changes. So please make a note that this is pi over 2 minus theta. It is not the other way around, pi over 2 minus theta, pi over 2 minus theta. And then the cofunctions just go with the function and their cofunction are always the ones that go together. You're not going to use the cofunctions a ton, but you absolutely will need to use them every once in a while. You do see them. I'm not going to say you never do, but they're not as popular maybe as the Pythagorean identities or some of the others, the reciprocal and the quotient identities. You will see these, but not a ton. When you do use cofunction identities, oddly enough, you're going to find that you use the even-odd identities right along with them. So the even and odd identities are having to do, actually, I kind of like to think of these with inverse functions, even and odd functions. We talked about this a little bit. If I have the sign of a negative theta. So I want you to picture what we talked about with inverse functions. So if I'm talking about sine inverse, right? And here's why I'm using this. Because if I have a negative theta, I rotate down into the fourth quadrant, right? So it's a negative theta. It's a negative rotation. It goes this way, down from the initial side. That's going to be the same as if I have a negative, so this would give me, as we know, the only thing positive here, always study trig carefully, the only thing positive in the fourth quadrant is cosine. So if I rotate sine down into the fourth quadrant or even in the third quadrant, that's going to be a negative value overall of the sine of theta. And now it's a theta because it's a reference angle we're using, but we know that the value of sine in that fourth quadrant is negative. Even if we rotated all the way over to the third quadrant, if we rotated back here, if my theta was, let's say, here, and it was negative, the overall sine value of that with the reference angle here with the x-axis would still be negative. So I know that the sine of a negative rotation of theta is going to be equal to the opposite of the sine of that theta. Okay? All right, so now it works the same way with its reciprocal function. So I can also say that the cosecant, we know that the sine and cosine, or the sine and cosecant are negative and positive in the same quadrant, so it's going to work the same way here. Cosecant of a negative theta is equal to the negative cosecant of theta. Okay? All right. So, then we have the cosine. We're going to do the cosine of negative theta is equal to the cosine of positive theta. Well, why is that? If we take a look again, If I have a negative theta, I rotate theta down here into the fourth quadrant, my reference angle will give me the value of the cosine function, but cosine is positive there. So even though it would be a negative theta rotation, it's going to have the same value as if it were just a theta in the first quadrant as its reference angle. So cosine of negative theta is the same as the cosine of theta. And then even if we rotated into the third quadrant, if we went back here, negative theta, okay, we'd have that reference angle. Well, cosine would be negative, and then if we rotated this way, that would still be negative. So either way, when you have a negative theta, it's going to give you the positive cosine value. All right, and then, so then if I have cosine, I can also say the same thing is true about secant of negative theta, and that would be just equal to the secant of theta. And last but not least, tangent of negative theta. So the tangent of negative theta, remember tangent and sine work the same way. So the tangent of a negative theta is going to be the same as the negative tangent of positive theta. And then the reciprocal function, the cotangent of negative theta, is equal to the negative cotangent of theta. Okay, so there are your identities, and these are going to be very important for you to know. You will have to memorize them and learn these, and the only way to do that is going to be with practice, and we'll make sure to get you plenty of that. No worries there. Okay, let's do some examples. So this first example, some of these you're going to find you can do them with some of the techniques that we've already used in Chapter 4. But I'm going to try to throw in some of the trig identities so that we can see how they're going to start to be used. So first of all, we've got the cosecant of theta equals 7 over 4. So we want to find the sine of theta. Well, we can use the reciprocal identity. We know that the sine of theta is equal to 1 over the cosecant. So I know that that's 1 over, the cosecant is 7 over 4, and 1 divided by 7 over 4 is the same as 4/7. So we're seeing that reciprocal identity come into play. But yes, if the cosecant of theta is 7/4, you know that the sine of theta is just the reciprocal 4/7. Okay, in letter B, if the secant of x is 5/4 and the tangent of x is 3/4, find the sine of x. So I know that the secant is positive, and that's the reciprocal for cosine. I know that tangent is positive, and so the only place where those two things are positive, where cosine is positive and tangent is positive, is going to be in the first quadrant. So because I have these ratios, I'm going to draw a first quadrant angle, and I guess we'll call this x instead of theta for right now. And we want to find the sine of x, so I need the opposite and the hypotenuse. Well, one thing they tell me is the tangent of x is 3/4. And I know that the tangent is really sine over cosine. So sine of x over cosine of x. And then I also know that the secant is the secant is 1 over the cosine of x, and that is going to be, instead of the secant of x is 5/4. So I would know then that the cosine of x is 4/5. Now, all that being said, we can label this triangle. If I know the tangent of x is 3/4, I know that's opposite, which is 3, over adjacent, which is 4. And using Pythagorean theorem, like I said, you could easily find that hypotenuse. But just to verify, they also tell me that the secant is 5/4, which is 1 over the cosine. So the cosine would be 4/5. And so then that is adjacent over hypotenuse. And so we can kind of see how those identities get verified. So now, really easy, if we want the sine of x, we know that that is opposite over hypotenuse, and that is 3/5. And could we have figured that out with talking about these reciprocal functions and how they work? Absolutely, yes, we could. But I'm just trying to get those wheels started to see how these are going to all work together and kind of verify, get you to understand how they can work together, because you won't always just be able to do it using the techniques we used in Chapter 4. It's going to get a little more involved than that. So, all right, let's look at example number 2. It says the tangent of theta is -8. So already I know that tangent is negative. And the sine of theta is greater than 0. So that right there tells me sine is positive and tangent is negative. So if we were back in the days of Chapter 4, just a couple weeks ago, we would say, okay, tangent is negative and sine is positive only in the second quadrant, so I have a second quadrant angle. Triangle, and I'm going to draw that there. And here is my theta from the x-axis. So if I know that the tangent is -8, I can put that over 1. Tangent is opposite, which is 8, over adjacent, which is -1. Sorry, that does not look more true to form. But to find sine and cosine, I need the hypotenuse. And quite honestly, you can absolutely do Pythagorean theorem. I would know that, let's say, c squared is going to equal 8 squared plus -1 squared, which is 64, plus 1, that's 65, which is c squared. So c is the square root of 65. Nothing needed from Chapter 5 or those identities really yet. Okay, nothing new. But I'm going to show you how it can, kind of verify it, how it can work in just a minute. So now if I want the sine of theta, I have it. I can go to my triangle. The sine of theta is the opposite, which is 8, over hypotenuse, square root of 65. And we would rationalize 8 root 65 over 65. Perfect. And then cosine of theta would be adjacent, which is -1, over hypotenuse, the square root of 65. And we would rationalize that. And that would be negative square root of 65 over 65. So nothing really new needed there, but what I want to do is take a look at how I could use this using some trig identities and show you kind of some of the ways that we need to start thinking that are a little outside of the box. Okay, so we're given tangent and we need to find sine and cosine. So one thing that we can say is that if we know, and again, this tells me, these signs tell me I am in quadrant 2. So if I'm on quadrant 2, one thing I know, I'm going to try to work this towards sine and cosine. Well, I know that tangent squared of theta plus 1 is equal to the secant squared of theta. Well, they tell me that tangent is -8, so tangent squared is going to be -8 squared plus 1 is equal to the secant squared. And at this point, you guys, you don't have to worry about really writing this down. I'm really okay if you just kind of want to watch this, because I would totally be okay with you doing it this way. I'm just trying to show you again how these Pythagorean identities work. So you can kind of relax for a minute and just watch this if you want, or you can totally take notes on it because you will be doing stuff like this soon. Okay, so 64 then plus 1 is equal to the secant squared. So the square root of 65 is equal to the secant squared, or is equal to the secant, sorry, we square root that. So the square root of 65 is equal to the secant. Now, if we are in the second quadrant and we are dealing with secant, that's the same as that sine-wise, it behaves the same as cosine in the second quadrant. So Actually, this would have to be a negative square root of 65. So the secant of theta would be a negative root 65. Now I need to work my way towards sine and cosine. So I know that secant is really 1 over the cosine. And so 1 over the cosine is negative root 65. And so I could say that the cosine, then if I flip the right side, I'm going to flip the left, and that would be 1 over the square root of 65, negative, and then I would rationalize it. So it would be negative root 65 over 65. So there is the cosine that they asked me to find, right here. Now, if I want to find the sine, here's another way, again, more complicated, but for some of you, I just want to show you how this all ties together. So if I want to find the sine, thinking outside the box, kind of verifying each step is true, I know that the tangent of theta, which they've given me information for, is equal to the sine of theta over the cosine theta. We all agree to that? Well, they've told me in this case the tangent of theta is negative 8. I don't know the sine of theta, that's what I'm trying to find. And I know the cosine of theta, this looks nasty, but hang in there, is the negative square root of 65 over 65. But now, all I have to do to find the sine of theta is to cross multiply. Negative 8 times the negative square root of 65 over 65 is equal to sine theta. Negative 8, I'm sorry, both two negatives make a positive. I don't know why I put that. So 8 root 65 over 65 is equal to sine theta. Wow, using those identities, mind-blowing, right? A little more complicated for sure, but as you can see, those are the same things that we got from using that right triangle. Only now, hopefully, you're kind of seeing those identities, how they can work towards solving some of these examples. Okay, example number 3. If the tangent of theta equals 1.28, find the cotangent of theta minus pi over 2. So this, if we go back, is going to be one of our cofunction identities. Remember that the tangent of theta is equal to its cofunction of pi over 2 minus theta. The cotangent is equal to the tangent of pi over 2 minus theta. Well, what we have is the tangent of theta equaling 1.28. But they want the cotangent of theta minus pi over 2. So we're actually going to use, first of all, the even-odd identity. If what I want to use is the tangent of theta equals the cotangent of pi over 2 minus theta, well, I'm going to have to reverse that. So that's going to have to be the cotangent of a negative, if I reverse this, negative pi over 2 minus theta. If I reverse the order of subtraction, then I'm going to have to make this theta, or inside there, negative. So the tangent of theta, I know the trig identity says the tangent is equal to the cotangent of pi over 2 minus theta, but it wasn't set up how I needed it. So if I do this, if I reverse and say cotangent of negative pi over 2 minus theta, reversing what I have up here, this is the use of the even-odd identity. Reversing the even-odd identity, remember it says, let's go back up here, and a lot of times these work together. It says, this one right here, the cotangent of a negative theta, and in our case that theta is a quantity. It's now pi over 2 minus theta. That is equal to the overall opposite sign of cotangent. negative cotangent of theta. So what I have now is that this is the negative cotangent of pi over 2 minus theta. Well, the cotangent of pi over 2 minus theta is equal to the tangent of theta, but I bring down that negative, so the negative tangent of theta, that's the negative of 1.28, so my final answer is negative 1.28. And what I used here, right here, was the use of my cofunction identity. And a lot of times these two are used in conjunction with each other. Okay, so going back through this, let me get this right here. Okay, so right here is where I reversed the order of subtraction and made it opposite. Actually, let me get a different color. Right here is where I reversed the order of subtraction and made essentially theta negative. And my even-odd identity says that when I make that negative, it now makes all of cotangent negative, and it's the negative cotangent of pi over 2 minus theta, which is the order that I wanted that subtraction in. Then, using my cofunction identity, I know that cotangent of pi over 2 minus theta is tangent of theta, and because it was negative, it's now negative tangent of theta. And then through substitution, tangent of theta is 1.28, so my final answer is negative 1.28. Okay, so hopefully you were able to follow that. All right, so now the next thing we're going to move on to is simplifying and rewriting trigonometric expressions. These are not equations, these are just expressions. There is no equal sign. Okay, so we are not solving anything. These are just expressions that we want to make look simpler. And the way we're going to start out is, before we even do any, I'm going to write some hints for you. Some things to keep an eye out for, because sometimes we look at these and we're not even sure where to start. So some starting points. The first one is, here's a hint, something you want to try to do, is to start by writing, if you can. Okay, this is not staying still. Start by writing in terms of one trig function. Or in terms of sine and cosine only. We tend to work a lot with sine and cosine. So one way to try to simplify it is to try to write everything in terms of one trig function, or try to write everything in terms of sine and cosine. Okay? All right, another way to simplify would be to try to apply the identities or factor. Yes, you can actually factor trigonometric expressions. So it says here that some, we're going to write this down, some trig expressions can be simplified by applying identities and factoring. Now I'm going to run out of room. Sorry about that. Okay. So that's one option. You may just apply the identities and do some substitution, or you may be able to factor. And sometimes things will cancel when you can factor. Okay. Another thing that you might find, you can simplify some trig expressions by combining fractions, which I'm sure you're excited about. I know y'all love fractions. Okay. So that's another option. And then there's a last option that we actually do use quite a bit, honestly. Okay, so look for this. When the denominator is of the form 1 plus or minus u, and u might represent a trig function, or u plus or minus 1, you might multiply the numerator and denominator by the conjugate of the denominator. Okay. And apply a Pythagorean identity. That actually comes, I forgot about that. And apply a Pythagorean identity. Really needed more room for this. Okay. All right, so these are 4 things that you really can't even picture yet because you haven't used them, but we're about to, and these are things that you can kind of look back and say, and they're just things that you probably are going to find yourself doing on a regular basis to simplify and then eventually to solve some of these trig equations and expressions. But like I said, today there are no equations, there are no equal signs, so we're just simplifying. So let's look at the first one. It says to simplify the cosecant times the secant minus the cotangent. So to simplify, again, our goal is to write this as simple as possible, maybe in terms of 1 trig function, maybe 2, but usually just 1. So to do this, we start kind of thinking, and guys, get used to, trial and error. You might try something and realize, gosh, this isn't getting any simpler. This is looking more complicated, and you have to erase and start over. What do I always say? You're getting sick of hearing it. It takes practice. There's no shortcut to that. It just is going to take some practice and getting used to, or you will absolutely not feel comfortable doing these. So cosecant and secant minus cotangent. So if I want to simplify this, I'm going to remember that, hey, cosecant is 1 over the sine of x, or theta. And then I know that secant is 1 over cosine of theta, right? We try to write in terms of 1 trig function or in terms of sine and cosine. We can do a lot with sine and cosine. And then cotangent, I know, is the same as cosine over sine. Okay, so now I've got it all in terms of sine and cosine. So now I've got to be able to work with fractions. And so I have 1 over sine theta cos theta minus cos theta over sine theta. Okay. So what I need to do is get a common denominator. So sine theta cos theta and sine theta, my common denominator, right? We're going to take one of every kind of factor that we have. We have a sine, but we need a cosine in both. So I'm going to actually multiply this second fraction by cosine of theta, top and bottom. And so now I have 1 minus cosine squared theta over sine theta cos theta. Okay, so I'm all in terms of sine and cosine, but now I'm seeing something that might look a little familiar. 1 minus cos squared. if you go back up, whenever you see one of these things squared with a 1, that should maybe start, hopefully that's going to start signaling to you Pythagorean identities when you see things squared. So I have sine squared theta plus cos squared theta equals 1. I have sine squared theta equals 1 minus cos squared theta. Okay? This is exactly what I'm looking at in the numerator. If we go back, I have 1 minus cos squared theta. I know that that's sine squared theta. And it's over a sine theta cos theta. These get kind of fun. If you let yourself practice, they get kind of fun. So then I love canceling. Sine squared cancels, and I'm left with a sine. So that's all gone. I'm left with 1 sine theta. Top and bottom, right? Sine cancels with sine. I'm left with 1 sine theta over cos theta. Well, sine theta over cos theta, that's a quotient identity. That is tangent of theta. So the value of this expression right here, cosecant of theta minus cotangent of theta, it is tangent of theta. How fun is that? I'm telling you, these are a lot of fun. All right, here we go. Next up, we have, to simplify, again, no equal signs, the sine squared of x times the cos squared of x minus the sine squared of pi over 2 minus x. So as I'm looking at that, there's some different things we could do. And again, it just takes practice, which I've had a lot of. But as you start to play around with these and you don't get very far, erase and start again with something else. But I want you to take a look at this. The sine of theta, or the sine of pi over 2 minus x. That's, if you go back to those identities, that's exactly what we need. The sine of theta, or the sine of pi over 2 minus x. That is the same as cosine right there. So knowing these identities, I can substitute in. I can say that this is the same as cosine of x. So here's what I have. I have sine squared times sine squared of x. Write that a little better. I have sine squared of x times cosine of x minus cosine of x. So I want to simplify this. Well, in each term, I have a cosine of x. So I'm actually going to factor it out. Even though this is trig, these are going to be very algebra intensive. You have to know a lot of algebra rules, what you can and can't do. Oops, did a theta. So if I factor out a cosine of x, I'd be left with sine squared x minus 1. Now, this sine squared of x minus 1, it looks super familiar, but you've got to go back and double check. With subtraction, order matters. So let's go back. There's a squared in there. So Pythagorean identities, I see that I have 1 minus sine squared x. Oops. Right here, I've got 1 minus sine squared, but not sine squared minus 1. But if I reverse the order of subtraction, that's okay as long as I make it negative. So I'm going to come back. Sine squared x minus 1 isn't the order I want, but I can say that's the opposite of 1 minus sine squared of x, and that's the negative cosine squared of x, which is being multiplied to cosine of x. So that is going to simplify to the negative cosine cubed of x. Okay? All right. So that is simplifying down to, we got from sine squared cosine minus sine of pi over 2 minus x to negative cosine cubed of x. All right, let's do a couple more. We're going to simplify the sine of x cosine of x over 1 minus sine of x minus 1 plus the sine of x over cosine of x. So this looks kind of tough. We've got lots of things going on, but essentially at the end of the day, this is two fractions being subtracted. And when you have that, you need a common denominator. So I'm going to take one of each factor. my common denominator, my least common multiple, is going to be 1 minus sine of x and cosine of x. So I'm going to make sure that I have each of those in the denominator. So 1 minus sine of x over here, I'm missing a cosine of x. So I'm going to multiply it in the top. And over here, I'm missing a 1 minus sine x. I'll multiply that to the top here. And let's create some new fractions. So I now have sine of x times cosine squared of x minus, now look at this, you guys. These are conjugates. 1 plus sine x, 1 minus sine x. When you have conjugates, all you have to do is multiply the first and the last. So this becomes 1 minus sine squared x. And that is over cosine of x times 1 minus sine of x. Okay, so not done. This is definitely not simplified, but here's what I do see. 1 minus sine of x, if you go back up and look at your identities and just get used to it, you're going to be flipping back to those things a lot. 1 minus sine of x right here is equal to the cosine squared. 1 minus sine squared, rather, is cosine squared. So as I go back right here, 1 minus sine squared is cosine squared of x. So I have sine of x times the cosine squared of x minus cosine squared of x over cosine x times 1 minus sine x. In the top, I can factor out a cosine. I'm going to do that. So cosine squared. I'm going to factor out cos squared, and I'm left with sine of x minus 1 over cosine of x, 1 minus sine of x. Okay, and so now this cosine cancels with one of those, and I have sine of x minus 1 and 1 minus sine of x. I can cancel them as long as I have a factor of negative 1 hanging out. And at the end of the day, this simplifies to negative cosine of x. Okay? All right. You might want to pause and go back and watch that one again. But the key is to just start getting used to these identities, and the more you work with them, the more that happens. Okay, and number 7. Rewrite 1 over 1 plus cosine of x as an expression that does not involve a fraction. So this kind of looks pretty simple. It's only got cosine, not too crazy, but we want just, we want something that has no fractions. So it might look a little more complicated, but again, no fractions. So if I have 1 over 1 plus cosine, if I want to not involve a fraction, I need to kind of start to get rid of that 1 plus cosine of x. So I'm actually going to multiply by the conjugate, 1 minus cos x. And these are strategies you just kind of have to try and do. You have to know your rules of math. You have to know what you can and can't do without causing an imbalance or a distraction. So as I multiply the top and the bottom by 1 minus cosine of x, I get 1 minus cosine of x over 1 minus cos squared of x. So now that I have 1 minus cos squared of x, that is a trig identity. That's a Pythagorean identity. 1 minus cos squared is the same as sine squared. So 1 minus cosine of x is still in the top. In the bottom, I have sine squared of x. Okay, so now what I can do is I can split up the numerator and put those both underneath, or I can put them both over sine squared. So I can say 1 over sine squared minus cosine of x over sine squared. Okay, and so then I'm going to carry my work up here. I know that 1 over sine squared, well, the reciprocal function for sine is cosecant, so that's really cosecant squared. Minus, but I still have this fraction. If it was cos squared over sine squared, I'd be making that cotangent squared, but it's not. So again, you've got to be thinking outside of the box. Cosine of x over sine squared, I can split this up one more time. I can say that that is cosine of x over sine of x times 1 over sine of x, right? Using those math rules, using the things that I know to be legitimate to break them down. So now cosine of x over sine of x is cotangent of x. 1 over sine of x is cosecant. And I have cosecant squared of x at the beginning. So no fractions, completely rewritten. Cosecant squared of x minus cotangent of x times cosecant of x. Okay, and this takes us up through 5-1. So a lot in this chapter. This is not the night not to practice. Good luck to you guys. And if you need to rewatch any of this, I would highly recommend it. But go practice and see what you can do.